So, hi to all of you guys. First of all, I would like to know who already is familiar with DC, Dynamic Cryptographers. Okay, a few of you. Today I'm going to talk about a technical solution against data retention. I will put an emphasis on the current anonymization technologies and which problems they bear inside. And then I will introduce you the Dynamic Cryptographers technology or the idea behind it, and then tell you also about some advanced mechanisms behind this idea. And then I will speak about the implementations which I did within the last 10 months or so during my diploma thesis. And of course, also I have an agenda, sorry. And of course, I will give an outlook, what is possible, how should the future look like, and then we have plenty of time for questions. So I hope you brought some, or then you will have some. So what is the current approach of anonymization technologies? If people are speaking about anonymization, it's most of the time mixed networks or mixed cascades. And the two most famous representatives are Tor, Onion Router, and YAP. And they work as follows, more or less the same principle. There is a network or a compound of mixes, yeah, so-called mixes, and a sender can construct envelope channels, encrypted channels through these mixes to hide the fact who is communicating with whom. And if there are different sender, a second, for example, does the same, then from outside it will become very difficult to find out who's communicating with whom. So I guess everybody of you will already know about this idea. So what problems do we have? I will first start off with the weakest problem. Compared to DC networks, we have weak encryption as it's only computation theoretically secure. So a strong attacker might be able to break the encrypted channels and then unveil the identities of the users. This is not a current problem, but if we keep using stronger and stronger computers, this might become a problem very soon. But for the time being, it's good enough. And to be honest, I'm also using computationally secure keys only. It's just that DC offers the possibility to have better keys. The second problem that I would like to mention is the unknown anonymity set. So if you speak about anonymity, it's about hiding identities. And so sometimes it can be a little bit complicated or it can seem a bit strange to think about knowing the other participants of the identity set would be a good idea. But I think if you want to keep your anonymity in a good quality, you have to know your anonymity set. So you also have to know who other participants or which other users are using the anonymization technologies. Because if you don't know them, if you don't know the exact anonymity set, intersection attacks can be very easy. So if you have a strong attacker who can measure who is using an anonymity service or not, and then is regarding the traffic over the anonymity set, and then he can maybe detect on Tuesdays there are two guys speaking about one subject, and on Wednesday there's only one of them speaking, and this kind of subject appears, so it's probably one of them, or it's probably the guy that speaks on Wednesday. So this is the intersection attack, and this is possible if you don't know the anonymity set. So. And now I come to the biggest problem. The trust relies in the mixes. So normally you have a pass through 3 mixes. and you have to trust at least one of them. In general, the anonymity can be unveiled either if all the other users of the anonymity service work together, or if all the mixes work together. Now the question is, are the mixes trustworthy? And this is a point where I beg to differ, because what is if we have something like a malicious Tor servers net? Tor servers net is an organization who put a lot of money and effort into building up Tor servers. It's a great idea and a great organization. I support them because what they do, I think they are trustworthy because I know them, yeah. But what they do is they mark their servers as a family. So they stay, the people can choose a path through different families of mixed compounds. So, but what if an attacker put a lot of money in setting up Tor nodes without marking them as one family? Then the probability would be very high to have a path through untrustworthy nodes. Another problem that we also face probably in Germany also with our next parliament is data retention law. So if a law would enforce the operators of anonymity services to open up all the connections, all the mixing techniques that they are doing, then the anonymity would be easily unveiled, as you can see on this picture. Most of this depicts the Tor nodes, and about half of the Tor nodes are located in Europe. So if we have a European data retention law that would enforce the operators to open up all the mixings that they are doing, would have a big problem for the Tor service. So now I would like to come to the DC part of this talk, the dying cryptographers, which can be seen as a technical solution to data retention, because data retention cannot attack the anonymity. In DC networks, officially the DC networks are invented by David Chaum in 1988, and it stands for dying cryptographers, but by random it's the initials of his name. And it's a round-based message exchange principle where all the participants take part in one round to exchange exactly one message. So to make it even more clear, during one round, one participant can exchange or send a message, and all the other participants that are using the service at the same time help him to anonymize the sending process. And the idea behind DC networks offers sender and recipient anonymity. So how do we achieve sender anonymity? First of all, the participants would have to exchange keys among each other. Okay, is the car? Okay. So first, the participant would have to exchange keys among each other, and the more keys are exchanged, the better it is, because the anonymity set equals the trustworthy participants that share one key graph. So even if you don't know all of the other participants, maybe the probability, or not maybe, but the probability is high that there are many trustworthy other participants using the service, and it doesn't cost you anything to exchange keys. So, and if you want to do a DC round, you have to use a new key each round. So what people do normally is they exchange key generators instead of keys, and there they can use real random or pseudo-random bit streams. Of course, if you have real random bit streams, then you have very strong anonymity. If you pseudo-random bit streams, then you will face the same problem, that it's computationally attackable. So to display, to give you an example how a DC round could work, here you see 3 participants, P1, P2, and P3. And P1 is pink because he is allowed to send this round. You can see it indicated by the M1, it's the message 1, which is 5. So he wants to submit a 5 in this round. And he has exchanged a key with participant number 2, which is 1, and he has exchanged a key with participant number 3, which is 3. And at the same time, you can look at participant number 2. He doesn't send a message this round because it's number 1's turn to send. And the key that he uses with participant number 1 is the inverse of the key that they exchanged. And there's an algorithm to find out which one of the participants uses the inverse and which one uses the normal key. And the same for participant number 3. So what they do is they add up a local sum. Yeah, it's normal adding 5 plus 1 plus 3 equals 9. And the others do 7 and negative 11. And these local sums are transferred to the DC service. This is what can be observed by the data retention, but there is nothing, because these messages, these local sums are like one-time pads. There is nothing that is worthy to be observed. And the local DC service takes the local sums and adds them up to a global sum, and what comes out is the message that participant number 1 intended to send. To have recipient anonymity, the next step would be for the DC service to broadcast this message, this global sum, back to the participants. This way, the probability that the message is destined for one of the 3 participants is equal, so it's perfect. So I'll explain to you the sender and recipient anonymity of normal DC. But what I said is, like, a participant can change only one message, and the other participants have to send 0 or the neutral element. So what we also need to do is to find out which participant is allowed to send in which round, and therefore you need a reservation phase or a reservation and sequence of rounds, which is defined by the reservation phase and the sending phase, which are both anonymous, are defined as work cycles in the DC terminology. How does a reservation work? There are different methods to do a reservation. The one I chose in my implementation is called collusion resolution method. As I already stated, it's anonymous, and it's done as such that you have specially formatted DC messages, and you send them to the DC service and observe the result. And by doing that several times in a row, you can find out when is your turn to send. It takes a deterministic amount of rounds for a certain number of participants to find out the order of sending process. But are we safe now? No, not really. If you're only a passive attacker, then you can gain no special information by just observing the local or global sums. But if you are an active attacker, you can attack the anonymity by delaying or modifying the broadcast. So I will give you an example. The evil DC networks now would broadcast the global sum A to participant 1 and participant 3, but A prime to participant number 2. And they, like this, animation, and in round N. And if the evil DC networks observes an answer A prime prime to the global sum A prime in one of the following rounds, it can only be from participant number 2, because all the other participants did not receive A prime, but only A. So the evil DC network would know that participant number 2 was the original or was the real recipient for this message. And he also knows that the reply is A prime prime. So what is the solution to this problem? The solution is to take the old messages, the old global sums that each participant receives into account when generating new keys. There are two ideas to do this. There is this deterministic fail stop, which takes all the old history of received messages into account, and then there is also a probabilistic fail stop, which only takes into account the last message and the last key used. I'll give you an example how it could work. So a key, this is probabilistic fail stop. A key to the time for the round number t between participant I and j would consist of random number or the random key for the time t, and also another random number for the time t, which is b, and the key from the old round plus e, which is it's a secret exchange constant. It doesn't change, and I is the message character, the global sum, which was received in the round that just happened before. Fail stop keys would have unequally distributed global sums into causing result so unequally distributed global sums would cause junk on the global sums. So the attack on the anonymity can be detected because if you do not observe your message on the network, then you know that somebody attacked or maybe tried to attack the anonymity, and yeah, you can react somehow. The anonymity itself remains. The bad side is that the service becomes unavailable, because if there's once junk on the global sum, it will propagate into the following sums. So you also need to think about, if you design such a protocol, how to resync or how to get the service restarted. Yeah, the other attack, which can be next to attacks on anonymity, is the attack on availability. We have already seen that the anonymity is very strong within the DC networks, but the availability is quite weak on DC networks. So not only that we use a lot of bandwidth to exchange just one message, but the participants can send when they are normally not allowed. And as I just stated, this will cause junk in the global sums. And if we have normal DC keys, like in the animation that you just saw, then just one round is disturbed. But if you use those advanced key generation mechanisms, the following rounds will be disturbed as well. There are in theory already algorithms to unveil the attacker step by step and to exclude him, but therefore you need an extra network in parallel with the feature to be highly available. And the other bad thing is that transmission errors have the same appearance as attacks on availability. But there the countermeasurement is just to sign the messages, so you can detect whether somebody transmitted junk on purpose or whether it was just a transmission error. So to recap the introduction of DC networks, DC is a technology which offers very defined anonymity. The anonymity does not rely on trust in the service itself. It can provide information theoretical anonymity if you use those real real random keys. And the attacks on integrity and confidentiality are easily detectable. Of course, I have to mention the cons. It scales with difficulties, and the availability is easily attackable. But I mean, if you want to have anonymous communication, sometimes the availability can be put behind the quality of anonymity. So now the protocol and the implementations. In my diploma thesis, I designed a protocol which defines a reservation and sending phase. It allows the participants to join and to leave the service dynamically. So all the papers think about permanent participants, but in reality, participants want to go offline and drive through a tunnel, so you have to think about how to do that. And it allows variable message lengths, so people can decide, I want to send 2 characters or 3 message characters and so on. And it's designed to be very low overhead, as the method itself already consumes a lot of bandwidth. Secondly, the protocols allows on-the-fly key exchange. Of course, then the keys are pseudo-random bit streams, and they are digitally signed, so you can verify other participants' identities. So you can consider for yourself other people as trustworthy or not by telling the different signatures apart. And the protocol is open for different key generation methods. So, for example, the 3 of those which I already presented to you. The protocol as well rethinks on attack on the availability. So if somebody is disturbing the communication, as we already saw, the protocol is already automatically rethinking, and also does it as well if advanced key generation methods are used. The flaws of the protocol are that a determination of the attacker is not yet possible, as there is no management network available, and it's yet based on a central DC service. What I did as well is real-time, not real-time, but it's an implementation in Java. It's a library which implements the presented protocol as a service and as well the participants. And it automatically maximizes the key exchange graph, so you will be as anonymous as you can be within the set of anonymity of the participants. And it offers a nice API, so even if you don't really understand everything what I just said, you could use it and provide some anonymous communication for your applications. It provides normal key generation as well as these fail-stop mechanisms, but it's also open to new key generation algorithms, and they are quite easily pluggable. If DC --, that's the name of the implementation, sees errors on within the communication, it retries automatically to resend. So that's also nothing that you have to keep track of. And also here there is no extra management network, so also here the unveiling of the attacker is not possible yet. I also did some other implementations, which is Erlang DC. It's the same but in Erlang, as I'm a big fan of Erlang, and it's maybe less scientific and more hackable and more suited for this kind of problem. And what I also did is a multicast library, which adds up a multicast layer above this DC communication, because often the participants are not interested in all the global sums, but only in a few. So they can pick up a multicast channel and then only receive those messages for this channel. It's transparent. What I also did were some measurements. I measured it within the Planet Lab. The Planet Lab is a compound of scientific organizations. They put up computers in the internet, and it's more a study than a laboratory measurement, as I use the real internet. And I have only little influence on the participants, as they are all doing other tasks as well. And the only attention I paid to were choosing the participants locally, so the latency would be minimized. And now this big surprise: if you have 10 participants with fully exchanged key graph, 1 kilobyte message length, you have about 1 kilobyte per second per participant, which is not too much. But you have to compare what does it mean. If you trust those 10 participants as you would trust the mixes that you use in Tor, this means that you take a route through 10 Tor mixes. So it's the same quality of anonymity. And of course, if you take this deterministic deterministic fail-stop key generation mechanism, which takes into account all the message history, you end up by 2 bytes per second per participant, which is of course not very good. And the other algorithms are within the same magnitude. And I found out that it's not a bandwidth problem, but a problem of advanced key generation method. And DC networks are synchronous, so it depends on the support of every participant. And in general, the participant need about 40% of a round time for key generation. But the slowest participant always needed around about 80% of the round time. So they were very, very slow. So the idea now to counter this this problem would be to install hierarchical DC networks, where you have a very low quality DC network where the people could participate, and after a certain amount of time, if they prove that they can send the message fastly enough, they could step one level up to a DC network of a better quality, where they would do quality contracts regarding the speed in which they send. Of course, I didn't mention it in the slides, but the protocol also supports timeouts. So you can also define a timeout, and after, if the participants do not send within the timeout, they get kicked out, and the communication can continue. So little early, I come to the future of DC networks. It's my great wish to decentralize. It's possible, I think. I have some ideas from BitTorrents in mind to distribute the computation of the global sum. And what we need as well is the management network to unveil the attackers, to be able to exclude them. And of course, one could play with hierarchical DC networks and reputation systems to make the quality a little better. So, what you should take home is there are other anonymity services than only mixed networks. This is one of them. DC networks can offer a technical defense against data retention. So if a politician comes and says, like, data retention would be the solution to every blah 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 terrorist attack and so on, you just say them they would use DC networks and they would be safe, so never mind. And DC networks also, if they are not suitable for your daily communication yet, yeah, I want to emphasize yet, they can maybe be a building block within your application design, with your protocol design. So you have something which offers a high and deterministic degree of anonymity. And I think I'm already done a little early. Sorry for that. So now I'm open for questions. Yes.
Thank you so much for the presentation. It was really good. And if you have questions, just raise your hand and I will get around to you.
Sorry, something that I wanted to say before the question. Maybe I think here this one was the first one. No. Okay. So if you are interested in this research topic or in anonymity in general, please contact me and help me to develop this this method and this idea. That would be great.
Okay. Now to the first question.
Could you go into some detail on how you detect attackers through the management the management network, and why an attacker wouldn't be able to out the identity of another anonymous participant with this technique?
I didn't get the question 100%.
So if you have a malicious participant, an attacker who's injecting noise into the system.
Yes.
There's a management network.
Yes.
That allows you to reveal only the malicious participant. How exactly does that work?
Okay, the idea behind is normally there's nothing on the management network. You would only use it in times of trouble, yeah. So if you observe some noise, some junk on the global sums, people start to send trap messages, which are not really confidential. But as the attacker doesn't know when people are sending confidential network messages or not, it wouldn't be, maybe he would attack such a trap, and then it wouldn't be a problem to open up the keys for that round. And by opening up all the keys in the management network, it would be able to find out who was the one that betrayed the others. And of course, there can be two participants claiming, okay, because it's always two participants sharing one key, right? So there can be two participants saying, okay, I used key A, and the other one has said, yeah, but we said to use key B. And the others cannot know. So what they do is just that they stop exchanging keys, and by then they would continue to communicate. And if you observe global sums, junk in the global sums again, then again you would try to open up the keys on a trap message, and then there's again this probably the attacker and another participant, and there would also be key A and key B. So, and over the time, the attacker would stop exchanging keys with all the participants. So he would result alone and had no more influence. That's the. Did you get it more or less? Okay, no problem. Next question, please.
One question from IRC. How well does it scale? Have you tried with a couple of hundreds participants?
Well, I scaled up to 30 participants, and it became very. I mean, it still worked, but it became very slow. So that I think to perform 70 work cycles, I needed 14 hours. With the probabilistic key exchange, key generation method. So it's not good enough yet.
Okay, the way I understood I'm here. The more people you have participating in message exchanging, the lower the bandwidth per person gets. Is that correct? Like the more people you have participate, yes. But as you already hinted, you mentioned multicast. This disadvantage partly disappears if you have one too many communications.
I
right?
didn't get the last part.
Like part of this deficit disappears if you have one too many communications. So if you have some sort of broadcast or multicast is said. So actually, wouldn't it be very interesting to use this for stuff like Twitter or radio, video broadcasting, that kind of thing? Have you put any thought into that?
Yes, of course. Twitter is the first thing that comes into one's mind if you are designing such a example program, for example. So yes, that would be Twitter is a very good application. Another good application would be anonymous distribution of files, like exchange, peer-to-peer exchange. So, but therefore it would be even nicer to decentralize and to remove the central base. But yes, you're right.
When you have the different clients connecting to a DC network and using it like a substitute for Tor or Yap, and you have like your nodes which are providing the entry node, and you have like clients using it, and you're nothing doing to protect their IPs, because every client has to exchange keys with every other peer. So I know all IPs of all peers within the network. So I can tell if a client is using it and then blocking them as an evil attacker. So
okay, as I already stated, the service is yet centralized, and the key exchange itself also goes over the server. So the participants do not see each other's IP addresses, but only the key IDs. And they are relayed over the service. But the service itself can, of course, see all the participants using it. And if there are governance that want to block a certain service and you only have one central DC server, then they block it and then it's gone, yeah. But that's an availability problem. Okay. Over there.
Okay, the next question over here.
Okay, in one slide you have shown P1 to P3, where P1 was sending the number 5.
Yes.
And he has only got positive numbers, and the other ones had the opposite. So the question is, if he's only allowed to generate positive key numbers, then the person with the highest sum is the sender.
No, that was just the example for here. This one. So here you have the 9, the 7, and the negative 11. Only one participant has a negative local sum, and this is just to make it easy for you to understand. Normally, everybody would just sum up and then beforehand calculate the key a little bit different and use modulo something. So I only use positive integers.
Given unlimited bandwidth, how many users could you accommodate in one network?
As I stated already, at the moment the problem is not the bandwidth, it's the key generation time. So 80% of a round duration is taken by the slowest participant to generate the keys. And that's the biggest problem. So I also have to improve the key generation, maybe do it in C and not those slow programming languages.
Okay, any more questions from the audience?
First of all, thank you for your talk. I was wondering, you mentioned that there is an attack on the availability which slightly looks like an error in the package. And your solution, or your suggested solution, was to use signature on it. But as far as I understand the signatures, it would actually fairly reduce your degree of anonymity within the network. So how would you what would you suggest as a signature algorithm that won't reduce the anonymity?
So what you already assigned are the keys. So the users of the service itself are known, yeah, or are considered to be known. This is the advantage, also in my eyes. If they use the same key to sign the local sums, you can see what an attacker from outside could also see, which sender or which participant would transfer which local sum. There is no additional information. It's just cryptographically verified that that there is no external attacker in between the line modifying the data. So that's. Was that good enough, the answer, or maybe I didn't get your question right?
Fairly about it, thanks.
Okay, thank you very much.
Any more questions from the audience? If not, I want to thank you all for the patience and want to thank Klops for the really good presentation and give a big round of applause for him.
Thank you very much.